Welcome to Computer 101.
Have you ever looked at your laptop, your phone, or really any digital device and wondered exactly how it captures and remembers a single bit of information? Well, today we're going to unravel that mystery. We're stripping away all the intense complexity to focus on the absolute heartbeat of modern computer memory, the D flip-flop. Now, if you're totally new to sequential logic, you are in exactly the right place. We're keeping things step by step. By the end of this explainer, you're going to understand precisely how this microscopic mechanical camera captures data in slow motion.
To make this super easy, here's our roadmap. We'll meet the D flip-flop, pop the hood to look inside the circuit, break down its step-by-step operation, read the timing diagram, check out negative edge triggering, and finally cover how to avoid metastability.
All right, Section 1, meet the D flip-flop. Okay, let's dive right into this. To get a grip on sequential logic, we really need to define the star of our show. A flip-flop is basically a sequential circuit element that samples its data input, which we just call D, and it only changes its outputs at very specific times determined by a clocking signal transition. We call that transition an edge. Honestly, the absolute best way to think about a flip-flop is like a camera. It doesn't continuously record video, right? Instead, it captures a precise single moment in time. The clock signal is literally the shutter button. When the clock flashes, the flip-flop takes a quick snapshot of whatever data is waiting at the D input and just holds on to it.
So, what does this look like on paper? When you look at the standard symbol for a positive edge-triggered D flip-flop, you've got a few key parts. There's your D input for the incoming data, your Q output for the saved result, an inverted output called QN, and that little triangle at the bottom, that is your clock input. It's the trigger. Now, if you check out its truth table, it spells out the rules perfectly. You'll notice a little upward arrow under the clock column. That arrow tells us everything. It means the output Q will only update to match the input D at the exact millisecond the clock transitions from low to high. At literally any other time, whether the clock is just sitting at 0 or sitting at 1, the output totally ignores the input and just stubbornly remembers its last state.
Moving on to Section 2, inside the circuit.
So how does it actually perform this magic trick? Let's pop the hood of our digital camera and look at the actual anatomy that makes this memory capture possible. What's super interesting here is that a D flip-flop isn't just one solid magic block. It's actually built out of smaller components. It combines two internal D latches paired up with two inverters that are connected to the clock signal. Think of these two latches kind of like a high-tech airlock system in a spaceship. You have an outer door, that's the first latch, and an inner door, the second latch. To safely capture a bit of data without letting it just rush straight through uncontrollably, these doors have to open and close in a very specific, carefully coordinated sequence driven by that clock.
Which brings us to Section 3, step-by-step operation.
This is the absolute core of our explainer. We're going to slow down time and watch this dual latch airlock heartbeat operate step by step. I want you to mentally prepare yourself for two distinct mechanical phases in the clock cycle. In phase 1, the clock signal is low, which opens our outer latch. Then in phase 2, the clock signal flashes high, which slams that outer latch shut and pops the inner latch open. Let's trace exactly how this data flows. Okay, picture phase 1. The clock signal coming in is low, a 0. Because of that first inverter, the enable input for the first D latch actually becomes a 1, meaning it goes high. That means our first latch is wide open for business. Whatever data is sitting at input D flows right in. But look at what's happening at the second latch. Its enable input is receiving a 0. That inner door is firmly, securely shut. So the data enters the airlock, but it's totally blocked from reaching the final output Q. It just sits there, waiting.
And then, the magic moment happens. Phase 2. The clock signal violently changes from low to high. Instantly, the enable input of the first D latch drops to 0. That outer door slams shut. It completely blocks any new data that might be trying to sneak in, securing the exact bit that was just captured inside the airlock. Simultaneously, the enable input for the second D latch flips to a 1. The inner door opens up, it reads the captured data from the first latch and passes it straight through to our final output Q. Boom! The flip-flop just captured the exact value of input D just before the clock changed, and now it's holding it steady.
So, the crucial point you should take away from this is this foolproof two-step mechanism. When the clock is 0, latch 1 is open and latch 2 is closed. When the clock flips to 1, latch 1 is closed, making it totally immune to any chaotic changes happening at the input, and latch 2 opens to display the saved result. It's this exact, beautiful handoff that creates that precise edge-triggered behavior.
All right, let's jump to Section 4, reading the timing diagram.
Now that we know the mechanical secret behind the airlock, let's translate this into the language engineers use every single day. We're going to look at a visual chart showing this behavior unfolding over time, a timing diagram. Imagine those classic digital squiggly lines. Your data input, D, might be bouncing around somewhat randomly, but your clock is a steady, predictable ticking pulse. Your final output is Q. If you focus on the exact moment the clock line goes from low to high, that rising edge, that is where the action happens. If you trace that precise millisecond, and the D line happens to be high, well, your Q line jumps high too. And here is the coolest part. Immediately after that edge, the D line can drop down, go back up, drop again, and the Q line absolutely does not care. It remains perfectly flat, holding its value until the next rising clock edge comes along. The camera flash went off, the picture was taken, and the memory is locked in.
Let's pivot to Section 5, Negative Edge Triggering. Of course, in the world of digital design, there's always more than one way to trigger a camera. What if we don't want to capture data on the way up? Some flip-flops are just designed differently. While our standard positive edge triggered flip-flops change state on that low to high transition, we also have negative edge triggered flip-flops. Just like it sounds, these change state on the high to low transition of the clock signal. So instead of capturing the data when the clock pulse rises, they wait and snap the picture exactly as the clock pulse falls back down to zero.
When you're reading circuit diagrams out in the wild, you really need to know which is which. A triangle on the clock input means edge triggered. But if you see a tiny little circle, an inversion bubble, right next to that triangle, that bubble is the universal schematic sign that you are looking at a negative edge triggered device. It's a dead giveaway. But what actually changes inside our airlock to make this happen? Well, if we look under the hood, the entire behavioral shift is achieved by doing almost nothing. You literally just remove the very first inverter from the clock's input pathway. That is it. Just by taking out one inverter, we completely reverse the timing of the doors. Let's walk through it real quick. For this negative variant, when the clock is resting high at a 1, our outer airlock door is the one standing wide open. It's actively monitoring the input D, passing it into the middle of the airlock, while the inner door stands totally closed, blocking the final output. Then the magic moment, the falling edge, the absolute instant, the clock drops from a 1 down to a 0. The outer door shuts to block new inputs, and the inner door opens to pass that newly captured value straight to the output Q. It's the exact same airlock process, just synchronized to the downward take of the clock.
Finally, Section 6, Avoiding Metastability. Now, before you run off to build your own processor, I have to issue a pretty serious warning. To keep this memory system healthy, we absolutely must follow the strict rules of physics. If we don't, our crisp digital photos turn into a corrupted, blurry mess. Here is the danger zone. For a flip-flop to work properly, the input D must remain perfectly stable for a specific amount of time before the clock edge hits. We call this the setup time, or T setup. It also has to remain stable for a brief moment after the clock edge, known as the hold time, or T hold. Think about our camera analogy again. If your subject runs across the frame exactly when the flash goes off, you get a blurry, unrecognizable photo, right? In electronics, if the data input changes its value right inside this critical setup and hold window, the flip-flop gets completely confused. It might output a voltage that is neither a clear 0 nor a clear 1, but something hovering weirdly in between. This corrupted state is called metastability, and it is nasty. It can ripple through a circuit and cause an entire computer to crash. So stable data around the clock edge is absolute law.
And there you have it. We've successfully demystified the microscopic airlock that captures a single bit of memory. From that incredibly clever dual latch internal design to reading the timing diagrams and even understanding the physical limits of metastability, you now know exactly how a D flip-flop operates step by step.
Thanks for listening, and see you next time.